Okay, so this is a really great question. And in this video, I'm going to focus specifically on the first fundamental theorem of calculus, because if you understand the first one, the second one will make a lot more sense. So what does the first one say to begin with? Basically, it says that if you have what's called an accumulation function, and we'll talk about that in a second as well, but if you have an accumulation function, which really is an integral where the lower bound is a constant, so a is a constant, and x is a variable that increases as the input to the function, if you have that and then you take the derivative of it with respect to the input, you just get the function evaluated at the upper bound, or f of x, out as the answer. Another way of kind of thinking about this is that the derivative and the integral are in some sense the opposite of one another. So if you take, or the inverses. So just like if you take square root, that equals just x. Well, if you take the derivative of the integral of something, it's just that original thing, because the derivative and the integral cancel out. So that's one way of understanding, but it gets a lot more complex. So the first thing to understand is just looking on the inside here. I'll call this function capital F because that's what's typical. It's typical to use capital F for the accumulation function. First off, we need to understand what an accumulation function is. So basically, it's like a normal integral. It's just that instead of having a lower bound that's fixed and an upper bound that's also fixed, the upper bound is a variable. It's a function x, and we can change x. And basically, if we change the input, which actually represents the upper bound of the integral, if we change it, we will change the area under the curve from a to x. And whatever the area under that curve is, that would be like the output of the function for that specific x value. So an accumulation function is literally a function that accumulates area under the curve for different x values. And just to show an example of this, let me actually share my screen real quick. So if you look at this specific thing that I have here, basically the idea of an accumulation function is we have, I'll say, a certain output. And let me actually graph, or sorry, just a second. So if I graph the value, pay attention to this orange value. When my x value is 2, because I'm setting my lower bound to 2 as well, right? In my accumulation function, you always have to choose a constant lower bound. When I increase the x value, you can see I get a different area under the curve. And as I do that, the orange value here, basically the height of this orange value, that's the output of the accumulation function for a specific x value, or b value in this case. And the height of that orange value is always the area of this green section. So it's like you can kind of look at this orange function as a new function in and of itself, this orange function. But it like the height of the orange function in any spot always represents the accumulated area under the original curve. So there you go. That's a little complicated, but hopefully that makes sense. Now, what do we do with that? So that's just a normal accumulation function. With the first fundamental theorem of calculus, we are taking the derivative of an accumulation function with respect to x. So here, what's the definition of the derivative? Loosely speaking, it's the change in the output divided by the change in the input. And you take the limit as delta x shrinks to 0. So this is like rise over run, or slope. This is another way of thinking about the derivative. Now, here's the question. When we're dealing with an accumulation function, how would that work? Well, remember, if you increase the input by a little bit, so that's like delta x, a tiny change in the input, the question is, how much does the output go up? So in our case, because we're talking about accumulated areas, we're asking, how much does the area increase? Well, if you think about it, does it make sense that if I have a tiny delta x, we're basically adding, not exactly, but in the limit, it gets closer. We're adding a rectangle here. And if you think about it, the area of that rectangle is going to be the height, which will be f of x, like basically the original function here, evaluated at x. So it'll be, height, or like height in this case, which is f of x, times width, which is delta x. And then we take delta x. So I'm literally just saying the change in the area is like this purple function. And then hopefully you can see that if you actually work through this, the delta x, like if you actually take this limit, you can see that the output here would literally just be f of x. So yeah, the derivative of this accumulation function is actually the height here. And that makes sense. If you imagine shrinking delta x down to nothing, you would basically be adding a rectangle that has no width, or has an infinitely small width. So the amount of area you're adding is basically just the height. That's the way of thinking about this. So hopefully that makes sense. This is like the general intuition for why the first fundamental theorem of calculus is true and what it actually represents. What I'm also going to do, I'm also going to link down below to a 3 blue, 1 brown video that I'll link to the exact spot in the video that goes a lot more in depth in this with a really good animation. So be sure to check that out. But hope that helps.